I want to talk today about a concept in calculus that are called limits. I would like to introduce you to this so that when you do see it in calculus, it's not so unfamiliar. And now I'll begin with a definition. The way I'm going to define a limit is to say that as the x values on a graph, right, or in a function approach a certain value, we want to look at what's happening to those x values corresponding y values. We want to see what values that they approach. Now I want to talk about the notation. All right, if we're saying as x approaches some constant a, then we would denote that as the limit as x, the arrow means approaches, so the limit as x approaches that constant a. All right, so as x approaches a, what happens to y, right? Well, in the notation, we're going to denote y as f of x because we know them to be synonymous. Right? So as x approaches a, y approaches L, right? L is also a constant. It's denoted with a capital letter. So I'll put equals L into the notation. Now the way that you would say this is the limit as x approaches a, and you say of f of x equals L. Now there are two different ways that we can determine a limit. The first way to determine it is from the graph. Right? And I call that by inspection. In other words, you inspect the graph, you look at it, and you figure out what the y values are going towards, right, for a particular group of x values. The other way is if you're just given the formula for the function, then you can evaluate the function at that value of a. So you would just plug a in, substitute in for x as if you were evaluating any other function. Now, the downfall to that is that we can't always just plug a in, right? And the times that we can't is if it causes the function to be undefined, right? But we'll see examples of that later. So let's look at the first way, determining the limit from a graph. Right, here's the notation just rewritten. And here's a sample graph. Note that the 0.2, 3, that ordered pair is on the graph. Now, I'm looking at, so as I'm saying as x approaches 2, what's happening to those y values? Well, those y values are heading towards 3, right? Therefore, I'll say as x approaches 2, f of x, or y, approaches 3. Right? And then looking at the point on the graph 0, 0, I can say as the x values approach 0, now this is from both sides, then the y values, or f of x, also approach 0, right? So they're getting closer and closer, again, from either side, right? Now the notation for this, for the first one, it would be the limit as x approaches 2 of f of x equals 3, right? Since f of x approaches 3, we would say the limit equals 3. And then for the other one, it would be the limit as x approaches 0 of f of x would be 0 also. Right. Now the important thing, I've kind of alluded to this as I've been talking about this, that we have to be approaching the same y value from both sides when I'm looking at this. All right. So again, looking at as x approaches 2, I'm looking at the values that are just very close to the left of the 2, right? In other words, I'm looking at x is equal to 1.9, x is equal to 1.999, and those values are just a little bit smaller than 3, right? You can tell that from the graph. Right? And I'm also looking at the values just on the other side. So I'm looking at 2.01, 2.0001. So those values are getting closer and closer to 2 from the right side, right? And those values are a little bit bigger than 3, and they're getting smaller as we're getting at those x values are getting closer to 2. Those y values are getting closer and closer to being 3. That's what we're talking about with the limit, and it has to be that same almost 3 from both sides. All right. Now, it so happens in the first graph that the function is that exactly at x is equal to 2, the y value is exactly 3. But that's not always the case, right? We can have a limit even if we happen to not be defined exactly at 2. Let me show you the graph. Now in this graph, the point x equals 3, there actually isn't a point, it's an open circle. Right? But everything around it is defined, right? And those y values are going towards 1 from both directions. Right? So we can say formally that even though f of 3 is undefined, right? It's not defined on the graph, the limit can still exist. We would say that because the values from the left side are approaching 1 and the values from the right side are also approaching 1, the limit as x approaches 3 of the graph f of x equals 1. All right, now here's another example. We are defined at x is equal to 2, right? But notice that the point where it's defined at, it's all the way up at where the y value is 3. But that doesn't mean that that's where the limit is, right? If you look around at the y values for x is equal to, say, 1.9, 1.99, or 2.01, all of those are right around 1, right, from both sides. And therefore, I would say the limit as x approaches 2 of f of x equals 1. Now, what happens if we're approaching two different y values when we're looking from one side and then from the other? Right? So let's look at this. This is what's called a step function. Right? We might have seen this earlier in the semester. Right? And then looking here at the x values that are just smaller than 1, like 0.999, 0.99999, right? Those values are approaching 2. They actually here, because it's a horizontal line, they actually are 2, but that's not really relevant to here. Right? Then if we look at it from the other side, if we look at 1.01 and getting closer to 1, 1.001, 1.0001, right? All those values are 1, right? So we can say the limit from the right of x is equal to 1 is approaching 1. All right, now to write this in limit notation, the way that we say it when the values are just a little bit to the left of the x value that we're looking at in the limit, we call that the negative side of that value x, or the value a, if you want to think of it. In this case, it's specifically 1. We call that the negative side. Right? And then when we write this, if we're saying we're only looking at the one side of the limit, we say the limit as x approaches 1. Notice that superscript there. So it's the limit as x approaches 1 from the negative side, or sometimes we'll say from the left, of f of x equals that y value of 2. And then for the other side, we would say that that's the positive side of 1, all the values to the right of 1. We say the limit as x approaches 1 from the positive side of f of x would be the y values of 1. Right? So then we can draw a conclusion if we want to talk about what happens to the limit as x approaches 1 in general. Well, there's the formula for this. Now, we say the limit as x approaches a, right, just talking in generalities, of f of x, if it would equal the limit of L, capital L, if and only if, so purposely two f's there, if and only if both things exist, the limit as x approaches a from the negative side of f of x, if that's equal to the limit as x approaches a of f of x, right, and they both happen to be some value L, then that makes the limit as x approaches a in general of f of x also L, right? But if they don't approach the same value like we're seeing in this example, then we would say that the limit in general does not exist, right? And you would just denote that as DNE. Right? And then kind of pulling that together back to the example, we would say the limit as f of x, the limit as x approaches 1 of f of x does not exist, right? Because the limits from each side aren't the same value. Now the other way, remember the first way was the graph, the second way was by looking at the function. Right? Then, for example, right, we have here the limit as x approaches 1 of a particular function. There's no denominator, right? There's no kind of conflict as far as where this is going to be defined, where it's not going to be undefined anywhere, right? So I can just plug in the 1 into this function and evaluate it, and that's going to give me the limit, right? So plugging in, simplifying, 3 plus 4 minus 9, 7 minus 9 would give me -2. Let's look at another example with a denominator. All right, now in my head, I'm plugging in the 2 into just the denominator just to get an idea of what I'm dealing with. I'm seeing that it's 2 minus 1. 2 is not going to make the denominator 0. And therefore I can just plug 2 into the whole thing and evaluate this limit. All right, so 2 cubed minus 3 over 2 minus 1. And of course I'm going to simplify this as much as I can. I have 8 minus 3 over 1, and of course I'm going to simplify that to 5. I'm not going to leave it as like 5 over 1. All right, let me show you an example when there is a problem. right? And how we're going to manipulate the function. Right. Now, if we have a limit as x approaches 5, right, and in my head I'm looking at the denominator, if I plug in 5 into this, it's going to make the denominator 0. It's going to make it 5 minus 5, right? All right. So I need some kind of a tool to simplify this so that I don't have that conflict of the denominator. And in this case, the trick that I'm going to be able to use is factoring. There'll be other tools that you'll use. This is the only one that I'm going to show you in pre-calc. You'll see other ones in calculus when you'll see other formats of functions. All right, so just kind of reiterating what I'm saying, if we plug in now, the function is going to be undefined, and you can see that in the denominator. All right, so instead what I'm going to do is I'm going to factor out the numerator. And it factors out to x minus 5 times x minus 1. And notice in the numerator and denominator, now I have a common factor of x minus 5, and I can cancel those out. Right? Then what's left, notice I'm still, when I'm just manipulating the function, I'm carrying that limit as x approaches 5 with me. I'll do that until I actually do the plug-in. All right, so now what I have left after I cancel out the x minus 5s is I have the limit as x approaches 5 of just x minus 1. Now I don't have a conflict. The 5 is not going to make anything undefined, and I can just plug it in. So I plug in, I have 5 minus 1, and the limit is 4. All right, so we're plugging in, and let me just kind of say, I'm saying formally what I was just saying before. Notice that once I plug in the value, like for the first one, x approaches 1, when I plug in the 1, then the limit notation goes away. All right, and that happened here when I did the test plugin, and that happened here when I did the final plugin.